Good day, stat students. So today we're going to go over chapter 7, part 2. So this is the second part of probability. The first thing that we're going to talk about is the intersection of two events. So there's two ways that we can show this, the intersection of two events with regards to notation. The first way is that we could use the word and. This is the most popular way currently. And so if you saw A and B, and A is an event, B is an event, that means that that's the intersection of event A and event B. You could also use set notation that has this upside down U, and that was used quite some time ago, and that was more popular then, and that has become less popular now. But if you ever see it, there you go. Talking about the intersection. So, example, we flip a fair coin twice, and let event A be defined as getting exactly two tails. Event B is defined as getting at least one tail. At least one tail means one or more. Here's the Venn diagram for it. Okay, and there starts to show us then where exactly is the intersection. And so notice this is, let me get my pen out. This is where the intersection occurs. It's where they overlap, right? It's where they overlap. And so this would be the intersection of A and B. So both events A and B occur, okay? And so excuse me, the intersection of A and B would be equal to TT. All right. So that satisfies this one, getting exactly two tails, and it also satisfies this one. Nothing else satisfies both. This doesn't give us two tails, this doesn't give us two tails, this doesn't give us two tails, nor does it give us one tail. All right. All right, the intersection between two events is that both events occur. So the only way both events A and B occurs if two tails are flipped. That's exactly what I was saying. Okay. So the intersection of two events is that both events occur. So let's go to a different example. Let's say you have a bag with 3 white, 2 red, and 5 marbles, 5 blue marbles. All right, what's the probability of getting white, then a blue marble? All right, well, we have two events, okay, where we're drawing a white marble, the first event. The second event is that we draw a blue marble. Okay, the only way that both happen is if we have W and B. Okay, so the only way that's going to happen. All right, we'll get to that that kind of stuff here in a little bit, but it was with regards to figuring out the probability. But before we actually do that, I want to make sure that we know the difference between these two things, okay? Because students get them mixed up all the time, all right? And so how is the intersection of W and B different than B given W? Okay, students mix this up all the time, all right? Let's make sure that we understand this. With the intersection of W and B, there's a chance that a white marble was chosen with the first event. There's a chance, okay? With B given W, with the first event, a white marble absolutely, with no uncertainty, was chosen. Okay, that's the difference between the two. First one, there was a chance that a white marble was chosen. With the second one, with the conditional, we know that a white one was chosen with the first event. That's the difference here. Okay, and actually, we're going to use conditional probabilities to actually help us to calculate the intersection between two events. So here is the formula for the intersection. So we have the probability of A and B. All right, and so notice here, we go first figure out the probability of A, then we multiply by the probability of, remember this, we're worried about the probability of B, but we know that A has already happened. Okay. So let's go back to our example. And what's the probability of getting white, then a blue, and without replacement? And what I mean by without replacement, when we select the first marble, it stays out of the bag. With replacement, we got the marble, we see what it is, throw it back in. Here, we're keeping it out. So, probability of W and B, white and blue. That would be the first, the probability of white. So what would be the probability of white? Well, how many white marbles do we have? We have 3 out of a total of here 10. So we have 3 out of 10 for the probability of white. That was the probability of drawing a white with the first marble, with the first, with the first marble, you can say. And then times the probability of blue, given that we drew the white marble already. So times the probability of blue given white. So how many blue marbles are still in the bag? 5 out of how many now? Total of 9 marbles, right? Because we took one out. We had a white one chosen the first time, so there's only 2 left there. So we have a total of 9. And that turns out to be 1/6. And I just rounded it to 0.167 because it's actually 0.16 repeating. Okay. So note mathematically that the probability of A and B is equal to the probability of B and A. So we can flip these around. Okay. This is one of those things that we can flip around and they are equal to one another. Okay. So we just found out the probability of A and B was this. Well, if we flip things around, we could also flip this conditional stuff around, okay? And we also get that. And so this is going to play a part when we talk about Bayes' law. Some call it Bayes' rule, all right? All right, so let's show it. What's the probability of getting blue than white without replacement? Well, what's the probability of blue with the first marble? Well, let's see, probability of blue. Remember, we're back to here. We're back to 3 white. So we have 5 out of 10. All right. So that's what I have here. 5 out of 10. Probability of blue. And then what's the probability of white given blue? Let's see. Probability of white given blue. Let's see. We have 3 out of, remember, now we're down to 4. Okay. And that means we only have 9 marbles left in there. So we have 3 out of 9, which I have here. Probability of white given blue. And what do we got? 0.167 again. Okay. So notice they are exactly the same. All right. We could also use our tables here. And actually using the tables, it's real simple because each cell is representing an intersection. For instance, this right here is representing this, the intersection between, yes, they live on campus, and males. Okay. This is representing what? Females and no, meaning they live off campus. So there's 6,400. That's not the probability, that's the number of. Okay, that's the intersection, not the probability of the intersection. That is the intersection. Okay, and you can think of it like this: is that where do they cross? Right? Where do they cross? Where does N cross with F? Right here. So there's 6,400 females that live off campus. Okay. So if we go back to this one right here, the probability of male and yes, well, we got 4,800 out of a total of 20,000. And there we go, 0.24. Probability of F and N, female and living off campus, well, we got 6,400 divided by the 20,000, we got 0.32, 32%. So using the table is pretty simple. Now, could we use this formula? Could we use this guy right here, even though we have the table right here? Yes, we can. Okay, so let's see, the probability of male, that would be 10,400 over 20,000. So you're going to see that for the first term. All right, probability of yes given male. So given male, so given that we know that a male was chosen, okay, given that we know that the male was chosen first, what's the probability of yes? So let's see. So we have 4,800 out of 10,400. And notice what happens here. The 10,400s cross out. We're left with 4,800 divided by the 20,000. And what do you get? 0.24. You get exactly this right here. Oh, I kind of did a boo-boo there. There we go. You get exactly the same thing. All right. So that works for all cases. Some people like to think of that we could do a bit of a shortcut when we have the intersection between two independent events. Okay, so this formula works if the events are dependent or independent. Okay, this is just a bit of a shortcut. If we know that the two events that we're looking at are independent of one another, what that means then is that the probability of B given A is just simply equal to the probability of B. Remember, that is the definition of independent events. Okay, and so if we do a little substituting here, so we know that this right here is equal to that. We substitute it into here, and what are you left with? You're left with the probability of A and B is equal to the probability of A times the probability of B. That's if they're independent of one another. So let's go back to our example. What's the probability of getting white and a blue marble, but with replacement? So we're throwing the marble right back into the bag. Well, since we replace the marble each time, the probabilities are not dependent upon what was previously selected. So the draws are independent of one another. So that means we could go ahead and say the probability of the intersection of white and blue is equal to simply the probability of white times the probability of blue. Okay, so what's the probability of white? Probability of white, 3 out of 10. But after we got it, we look at it, throw it right back into the bag. And what are we left with? As far as blue marbles, 5 out of 10. And there you go. You multiply across, you get 0.15. All right, so remember, that only works when the two events are independent of one another, and we know it. All right. All right. So if we start with this, okay, and we do some simple algebra, okay, we can now have a formula for the conditional. So in other words, the probability of B given A, if we divide both sides by the probability of A, okay, so divide by the probability of A over here, these cross out, and then divide by the probability of A over here. That's what I mean. Okay, what do we get? We get that formula right there. Okay, so you can also have this flipped over here. We could figure out the probability of A given B, and things just switched here in the denominator. Okay. All right. So this was an old slide that I showed before. Okay. Back when we had the probability of n given m. Okay, and we used our tables, and we said, let me remind you what we did here. So probability of n given m. So given m, so we had 10,400. What's the probability of n? Well, how many n's do we have? We got 5,600. So we have a probability here of 0.538. Okay, so we know that's the probability of n given m. Could we go ahead and use our formula, though, that I just showed you to figure this out? Well, that means this should be equal to the probability of n and m over the probability of just m. So let's see the probability of n and m. Can you figure that out? See if you can figure that out. Let's see here. Here's the intersection of n and m. We would have to divide that by 20,000. So that would be the numerator. The denominator would be the probability of m. That would be 10,400 over the 20,000. So we got 5,600 divided by 20,000 from the numerator. Denominator, 10,400 divided by 20,000. Oh, guess what happens here? If you do, the reciprocal here, what's going to happen is the 20,000s can't cancel out. What are you left with? 5,600 divided by 10,400, and there you go. Got the same answer. A little bit longer, it's a little longer, a little more drawn out when you do it like that, okay? But you can do it like that, all right? So if anything was lost on you, please go back and make sure that you understand those all those steps there, okay, and how they all relate to one another. Let's talk about the union of two events. So there's two ways to present the union. You can use an or statement, so A or B, so events A or B, or you can use set notation where you have this U-looking thing. And so what exactly do we mean by A or B? Well, that means that event A has occurred, or event B has occurred, or both the events have occurred. All right. And so let's take a look at our Venn diagram. Here's event A. Here's event B. Here's the intersection. And so the union of A or B would be all that. Okay? Would be all of it. All that stuff in gray. So the Venn diagram is going to help us to understand why the formula is what it is. So here's the probability of A or B. Okay? So if we start with the probability of A, and we go ahead and add it to the probability of B, I'm sorry about that, what has been counted twice essentially? So here's A, here's B. What's been counted twice? Yep, the intersection, right? So if it's been counted twice, we got to take it out once, okay? And so the formula then is the probability of A plus the probability of B minus the intersection between the two. And again, we're subtracting the intersection because it was counted what? Counted twice. Okay. So here's an example that I showed before. We roll a six-sided die once. We'll let event A be equaling an odd number, B an even, C a prime number. Okay. So here's the possibilities for each one. So we know that the probability of A is equal to a half, probability of B is equal to a half, probability C is equal to a half, because each one has three possibilities here out of what? 6. Okay. So we have 3 numbers that satisfy each out of a total of 6, so a half. All right. So let's go figure out the probability of A or B. All right. Probability of A is what? We just said it was 3 out of 6. All right. Here's the probability of A plus the probability of B. Okay. That's 3 out of 6. And notice I said the intersection of A and B is 0. Why? Because there's, notice with regards to A and B, there's nothing like about them. There is no intersection. So we would have said that's 0. So the probability of A or B happening, no, that's 1. Okay. So either we're going to roll a, think about it, either we're going to roll an odd number or we're going to roll a even number. Okay. Makes sense. All right. What about the probability of A or C? So A or C. All right, so we start with the probability of A. That's 3 out of 6. Probability of C is 3 out of 6. Minus, well, what's the intersection here? Okay, what's the intersection? Let's think about this. So let's see here, A and C. The intersection, we have 3 and 5 over here, and we have a 3 and a 5 over here. So that's what? 2 out of 6. Okay, that's 2 out of 6. And so we would have to subtract that because that was basically added twice when we added the probability of A and C together. So we got to take it out once. All right, and what's our answer here? 4 out of 6. Okay, 2/3, right? 0.6 repeating. How about B or C? Okay, B or C. We would start with the probability of B. That would be 3 out of 6. So we got it there. Probability of C, again, 3 out of 6. What's the intersection between the two? Okay, what essentially got counted twice? What got counted twice was the 2. And so there's 1 out of 6. We would subtract that out. And so we have 5 out of 6. Okay, let's go ahead and use our table to figure out the union. So let's say that we try to figure out the union of M or N. Oh, I'm sorry, I said that. I said that wrong. Not the. Oh no, that's right. We're figuring out the union. I'm sorry. Let's figure out the union of m or n. All right. So here's our formula. That would be the probability of m plus the probability of n minus its intersection. So what's the probability of m? Let's see. That would be 10,400 out of 20,000. What's the probability of n? That, let's see. So here's n. That would be 12,000 out of 20. And then we got to subtract its intersection. What's the intersection of m and n? Looks like this guy right here. So probability of m, 10,400 divided by 20,000, plus the probability of n. There's the 12,000 divided by 20,000, and then here's the intersection between the two. Notice it's the intersection right here. It's in green, right? 5,600 divided by the 20,000. What do we get? We get 0.84 when you do the math. Okay. All right, let's talk about Bayes' rule. This is the last thing with regards to probability that I want to talk about. Some people also call this Bayes' theorem. So, believe it or not, you can figure out the probability of A given B by using the reverse conditional, by using the probability of B given A. It's kind of interesting. Okay, let me show you how. So we start with what we know about probability of A given B. What do we know? We know that based upon the formula that I showed before, that's equal to the probability of A and B divided by the probability of B. But remember what I told you earlier, is that we could go ahead and actually then say that the numerator, if the probability of A and B is in the numerator, we could go ahead and say then the probability of A and B is equal to the probability of A times the probability of B given A. Makes sense, right? So this right here is one form of Bayes' rule. Okay, this simple formula. Okay, I didn't mean to make a heart, but there you go. That's one simple way of looking at Bayes' formula, or Bayes' rule, I should say. Okay, so I just repeated it over here. So here's an example with regards. You are planning a picnic today, but the morning we know is cloudy. We wake up, we look outside, it's cloudy outside. Okay, based upon the records, 50% of all rainy days start off cloudy. Okay. We also find out that 40% of days start cloudy in this particular month. Also, this is an unusually dry month, okay? And it only rains 10% of the time, all right? So we could figure out the probability of A given B using this formula, okay, based upon this information here. So what we're going to try to figure out, what is the chance of rain, okay, because we're having that picnic today, right? So what's the chance of having rain, knowing that it's cloudy for this particular month, okay? Because all this stuff, okay, all these records are for this particular month, okay? So in other words, what are we trying to figure out? We're trying to figure out what's the probability of rain given that we wake up and it's cloudy. Well, okay, so we're going to use that formula right there, all right? And so looks like, oops, I didn't mean for all that to go away. So that means that that the formula would be the probability of rain times the probability that it's cloudy given rain over the probability that it's cloudy. And all that stuff is in the problem right there. So what's the probability of it raining this month? Well, let's see here. Looks like it's 10%. Oh, geez, I didn't mean to make all that stuff go away again. So we know it's 0.10. Okay. What's the probability of that it's cloudy in the morning and we know it rained. So 50% of all rainy days start off cloudy. Okay, so we know that what? That it rained, okay, and that what's the chance that it started off cloudy? That 50%. That right there is probability of cloudy given rain. And then what's the probability of it being cloudy? Well, let's see. We also find out that 40% of the days start cloudy. So that's 0.4. So 0.125 when we do the calculation there. Okay. So we can figure out the conditional based upon the opposite conditional. All right. Here's the thing, is that you can extend Bayes' rule or Bayes' theorem even further. All right. And that's by examining the probability of B, okay, the denominator. Probability of B can be figured out using the intersection between A and B, along with the intersection between the complement of A and B. So if there's just two events that could possibly occur, okay, believe it or not, you can figure out the probability of B, okay, kind of indirectly by using the what happens with the intersection with A and a complement. And I'll show you. Best way to do this is with a Venn diagram. All right. Here's a sample space, right? Here's event A. Here's the complement of A. Here's B. Okay. And so the objective here is to figure out the probability of B by using the intersection of A and B along with the complement of A and B. All right. And it's a little bit easier than what you think. So we're trying to figure out this circle right here. Okay. But we can't necessarily calculate B directly. All right. But what we're going to find out is that we could use A and the intersection of B along with the complement of A and its intersection with B. I'll show you. So again, we're trying to figure out this circle here. Okay. And what did we know about this right here? We knew that that is what? The intersection of A and B. So we have part of the circle here. Okay. So here's the total circle that we're trying to figure out. And here's part of it that we just figured out, A and B. So what we're left with is this part right here, okay, that we still have. And if we could combine that with the intersection of A and B, looks like we can figure out B then. Well, what exactly is that? Well, believe it or not, that is the intersection of the complement of A and its complement and B. So remember, here's A, okay, and that means everything outside of A is the complement of A. And so this part right in here, okay, what would that be? Well, that would be the intersection of the complement of A and B. Okay, and so if we start with probability of B and use those thoughts there, is that the probability of B is actually equal to the probability of A and B plus the probability of its complement in B. And now you got all of B now, and no more, no less. Okay, so that's another form of Bayes' rule right there. But we, believe it or not, we can extend it even further. Okay, so I just recopied it there. We could use conditional probabilities now with regards to this and that. So we can extend it out further. So we know that probability of A and B can also be what? Probability of A times probability of B times given A. And we can extend this guy out. All right, so the probability of complement of A and B would be equal to the probability of complement of A times the probability of B given the complement of A. I know it's kind of a lot, okay, but this is another form of Bayes' law, Bayes' theorem. It's right there, okay? So there's the first two. There's the third one that we just talked about, okay? And what I encourage you to do is that if you have more interest in this, okay, or if you are a medical student, because you will probably run into this law or this rule in medical school, is that you want to go ahead and check out pages 240 and 241 in the text. It gives you an example, okay, and it walks you through this right here, okay. And I think it might even use a probability tree to help you understand that also, okay. So I encourage you, if you have more interest in this, or if you're a medical student or you're future medical student, to check out uh, these pages right here in the text, and it'll go through an example with regards to this last one. Okay. All right. Thank you very much, and that ends our probability section.